the quasi-adiabatic relaxation of halos in various cosmological simulations.
Am I audible? I would like to thank the organizers for giving me this opportunity to talk about my research work. It's on the quasi-adiabatic relaxation of halos in the IllustrisTNG in Eagle simulation. So I'm a PhD, fourth-year PhD student from IUCAA. I work this work with Professor Aseem Paranjape. So we all know that in the standard lambda CDM picture of cosmology, the galaxies are surrounded by a large non-luminous halo, and it is generally understood like in the original structure formation, the dark matter evolves into structure and then forms a halo, and the galaxies form within it. So usually this is studied extensively using gravity-only simulations where only the gravity is assumed for evolving dark matter and to form the halos, and within these halos then galaxies are populated, or galaxy formation is done using some semi-analytical model in different way. So what we are interested is how the formation of galaxy in turn affects the dark matter. So we have seen just in the previous talk when Manoj has talked about like core class problem. So there also typically one extensively used gravity-only simulations to study this NFW profiles for the dark matter. But when comparing with observation, we need to also account for the variance. So we would like to see if there is any simple model that we can use to predict the effect of galaxy formation on the dark matter. So for this, what we use is this aerodynamic simulation, as many of the speakers have talked about. This aerodynamic simulations evolve cosmological volume with both gravity and also baryonic component with lots of astrophysical processes like galaxy formation through cooling and then star formation feedback, etc. So we such a simulation, and what we do is we compare halos from such a simulation with a corresponding another simulation where only gravity is there, and we see how the halos are different. So here, for example, if you look at this is one such halo from an Eagle aerodynamical simulation. The left one is the same halo in the aerodynamical simulation, and the right one is the same halo in the corresponding gravity-only simulation. We can see that in the halo simulation, the halos become noticeably compact, and also it becomes more spherical. Here we will focus more on this change in the density profile, the spherical average density profile, which will quantify how the halo, like whether it becomes compact or expands. So historically, most of the early works, in order to model this like contraction or in generally relaxation, they used a simplifying assumption of angular momentum conservation, circular particle orbits, and no shell crossing. Under such assumption, we can say that if a dark matter particle is at some particular radius Ri in the dark matter only simulation, in the hydrodynamic simulation, which includes the effect of galaxy formation, it will go to a radius Rf, which and because of no shell crossing, the total dark matter mass enclosed will be same at Ri in the initial simulation and the Rf in the final simulation. Not final, it's basically the gravity only and the hydro simulation. And this is related to the total mass enclosed within this, because the dark matter mass is same. So the only difference is coming from the change in the baryonic content, baryonic mass within that shell. So this model was early proposed, but later with various cosmological simulation was not found to be working well. So people have come up with some modifications, such as like this quasi-adiabatic relaxation, where this Rf by Ri is written as some function of Mi by Mf. For example, one simplest modification is taking a linear q times. So it's like Rf by Ri minus 1 is q times Mi by Mf minus 1. The reason it is taken in simple this q factor is because so that when Mi by Mf is equal to 1, Rf by Ri will be equal to 1. What this means is that when there is no change in the baryonic content within particular shell, then we don't expect some relaxation should have happened under this assumption of angular momentum conservation. So we looked at the halos from the IllustrisTNG simulation. So we take in IllustrisTNG simulation, we take multiple sample of halos selected by mass. So for example, here the first plot is selecting halos at around 10 power 11.5 H inverse Simpson halos. In TNG, the smallest box which provides the highest resolution. So here I have just shown a representative 20 halos. For each of the halos, what I'm showing is the Rf by Ri, that relaxation ratio, as a function of the mass ratio, the change in the total mass content within that shell. So for each of the halo, I calculate this quantity of relaxation ratio and mass ratio at different values of the radius, and the color here represents the radius at which the shell is present in the final hydrodynamic halo. Then I stack over the relaxation ratio and mass ratio at each radius to get a stacked relaxation ratio. We also stack in different way, like just stacking it at fixed MI by MF, so that we can extract a stacked relaxation relation. And already we see that if for different halo mass scales, we find that the relaxation relation, stacked relaxation relation shows some unique behavior at different halo mass scales. So we went ahead and used all the different three different LSSTNG simulation box. So we could get, we were able to resolve the halos at very small halo mass, like 10 power 10 H inverse emission, all the way to 10 power 14 H inverse emission halos. We were also able to get enough statistics by using the largest TNG simulation. And the right one is a similar study for the Eagle simulation, because in Eagle simulation there are only two boxes. We are able to explore a smaller range of masses, and we can see that for the largest halo masses, which is this black color, around 10 power 14 H inverse emission, there is almost no relaxation relation. There is almost no relaxation, that is RF by RA is almost close to 1. Whereas for the small, around this 10 power 12, 10 power 11, there is a strong relaxation happening in the halo, such that the relaxation radius goes all the way up to like 0.7, 0.6 for when the change in the mass is of the order of half. So one thing we notice here is that this simple Q equal to constant model, like Q equal to 0.68, Q equal to 0.33 model, can't model the this relaxation relation at especially in this mass scales, because there is an offset from when MI by MF equal to 1, RF by RA is somewhat offset from 1. I will come to this later, but right now if we try to fit with such an offset also, we are not able to get any good fit for this relaxation relation. Then, and also because there is a wide variation in the relaxation relation in this perspective, so we tried modifying this model. So what we did is we looked at the relaxation ratio and mass ratio, but at each radii across different halos, and we just stacked the relaxation ratio and mass ratio at each radii. Here the color shows the radii of the shell. So for each radii, we see that this relation between the relaxation ratio and mass ratio is close to being very linear, and this particular model of this Q1 plus Q0, this two parameter model fits well at each radii, but it can't fit well when applying for a globally. So here if you see that at a MI by MF of around like 0.98, for different radii, the relaxation radii is different, relaxation ratio is different, and at each radii it's well fit by a linear relation. And we went again and checked that across different mass scales in different halos, and we find that in all the cases the behavior is very different, but in all the cases the linear model gives a good fit. So I will go quickly over. So here we show that linear relaxation parameters Q and Q0 as a function of radii, and we already see that for except for the cluster mass scales, we find almost universal behavior for the Q1 and Q0, which we model by taking because it is in log, we model it by a linear fit. That is this, and this gives us a 3-parameter model for the relaxation radii. So with this, we find that this 3 parameters Q0 and Q1, we plot it as a function of halo mass. We find that for most of the halo mass between 10 to 12, this Q0 is roughly constant, which is the offset parameter. So the reason this offset parameter is something negative value rather than 0 means that RF by RA and MI by MF equal to 1, RF by RA is less than 1. That is relaxation happens even when there is no change in the mass. So this could be, this can be possible when there is a feedback effect that pushes away some of the gas outside the radii. So we then looked at how concentration and other galaxy properties affect this. So here also we see that with concentration, here the upper triangle says that when the concentration high, the Q0 magnitude of the Q0 is less, which says that for a halo with a higher concentration means it would have formed at an earlier time. So for such an halo, we find that the Q0 is less, which can be understood because the earlier formed halos would have had enough time for the feedback to have happened at an earlier time and the halo to have responded to it already, whereas the recent formed halos has not had enough time to respond to the feedback. So then we looked at this halo properties, the galaxy properties of like stellar fraction, and the second one is the star formation rate. With star formation rate, the thing that is, it's again consistent with our expectation that when the star formation rate is high, that is upper triangle, we see that the Q0 as a more negative value. That is because the current active star formation rate says that recent feedback says that the halo has not responded to such a feedback, and hence the Q0 is having a higher negative value. So we then I will conclude with how we can use this model in various when comparing simulation with observation. For example, when we have a simulation which gives the dark matter density profile in a gravity only simulation, we can use this model to predict the mass profile that we expect from a full aerodynamic simulation where the baryonic physics with feedback and all these things are included. So here I compare in the dashed line shows the prediction by this model taking the full dependence of the relaxation relation. And in the solid curves, I take for each of them, I take a different model. In this, the first one, I take this 3-parameter model with the Q0 values as function of mass, and this in the second one, I take this model with a fixed value of the parameters Q0, Q11, and Q10 and Q11 as. So here the Q0 is a small offset of that minus 0.05, and Q10 is close to 1, which is close to the adiabatic relaxation. And 0.5 is the slope parameter for the relaxation area. And here we compare this other that are well-known models like Naidin et al. 2004 and Kautan 2020, and the original Blumenthal et al., which is the standard adiabatic relaxation. We find that in comparing to all of the models, this full relaxation model of ours is able to produce a much better estimate of the dark matter mass profile that we expect with baryonic effects. And even for this 3-parameter model, which just constant 3 parameters universal, we see that in the outer region, most of the other models have a large, underpredicts the mass profile, whereas this model with just 3 parameters, a universal model, we are able to get a much better constraint, less than 5%, close to the expected mass profile for the dark matter in the aerodynamic simulation. With that, I will conclude. So what we did is we used the aerodynamic simulation Euclid and LSST to try to understand the physics of the relation, by looking at how it varies as a function of different properties. And in this way, we tried building an intuition like what are the key parameters that will drive the relaxation. And we proposed a model which can be used for various rotations of observations, where it can be used to fit the observation as a model. And in the future, we are also trying to explore further by varying, studying the relaxation as a function of different aerodynamical simulations with different feedback physics and other baryonic physics. And also, we would like to we are currently studying an analytical physical intuition for the relaxation. And thank you everyone for showing interest in this.
Questions?
So what was the, maybe you mentioned this, but maybe I missed it, but what was the range of masses that you looked at over all of the simulations?
So I look at from 10 power 10 the very dwarf scale halos to all the way to 10 power 14 H inverse M channel.
Right. And you saw that the variation in this Q0 thing is larger for the higher mass halos, whereas it's flat at the lower end.
This variation in which plot you're referring to?
The offset thing is flat at the lower end and varies more at the higher end.
It's in the lower end. This for this low mass halos, we see that it's offset from, like, when the MI by MF equal to 1. This RF by RI we expect to be close to 1, but it is offset from value. This is mostly seen for the low mass one. For the high mass, it's.
Thanks.
So, the parameters that you get for the Eagle model and the IllustrisTNG are the same, or you have to tweak for simulation?
Yes, it's like I have not compared for the dependence on the star formation rate and so on, because those are the things which likely to differ between the simulation. for the dark matter, the relaxation relation itself, even from this relation, we can see that it's closely similar. This blue ones and here this blue ones are the halos of same mass. And the reference model one is one, so it's the range of.
So the difference is, so there are few differences.
Yes. Yes. So here, if you look at in the like comparing between this yellow one and actually with Eagle, the low resolution one, we found that there is some difference which we can also see here. In Eagle here, I have not shown the exactly which box, but basically the lower one like 10 power 11 and 10 power 11.5, those come from the smaller volume box. That is not, it's a very small volume, so maybe the other effects has led to a different behavior. But the main Eagle simulation is consistent with the IllustrisTNG.
Last question.
I guess you showed this plot of M predicted versus true M for different models and your model in one of the last slides. So this is the entire dark matter mass and dark matter only mass in both hydrodynamical and n-body, right?
Yes. So
could you extend this to also, so for example, if I want to paint on an n-body, not just the dark matter mass effect of baryons, but also other masses, is that also included? And could you?
Yes, actually, so I have not mentioned. So in order to predict this dark matter mass profile that we expect after the galaxy formation feedback and all this thing, so we actually need to input the mass profile of the baryons. So we need, so for that we can like start with the gravity only dark matter mass profile and then use some other semi-analytical techniques or other techniques to make the baryonic mass profile, and we have to combine these two mass profile in order to make this prediction. So in technical, in principle, we can just make the total mass profile.
Okay, we can thank the speaker now, and we'll move to the next talk.